Okay, so now that we understand a little bit more about the polymorphism-aware phylogenetic models, let's have a closer look at the model. So the polymorphism-aware phylogenetic models, or POMOs, state space is defined based on two quantities: the number of individuals in the population and the number of alleles in the population K. With these two quantities, we can define essentially two types of states: the fixed or the boundary states, in which all the individuals in the population have the same allele, AI, it can be A0, AK minus 1, and essentially this represents an homogeneous state. But we can also have polymorphic states, in which some individuals in the population may have one allele and some others may have a different allele. And of course, during time, we can jump from one type of state to another type of state. But how do we do that? So essentially, we use population processes to allow state changes. And one of such processes are mutations, of course. And the mutations we represent using the parameter mu. So as you can see here, this is Q, an element of the rate of the POMOS rate matrix. And we have a monomorphic state here, meaning a fixed state in which all the n individuals in the population have the AI allele, and after some time I'm reaching the state where one individual have the AJ allele. And we know that this process can only have occurred by mutation, so I'm introducing a new variant in the population. So again, I describe this using the parameter mu from the allele AI to the allele AJ. Often we use a reversible mutational model. So instead of actually using the mu parameter, we break the mu parameter into a product, the rho times pi, in which the rho represents the exchangeabilities between any pairwise combination of alleles, and rho the base composition of the allele that we are reaching. And the reason because we do that is this facilitates obtaining formal quantities with POMOs, meaning obtaining the stationary distribution, the expected divergence, the expected heterozygosity, and that's why we use it. Still, it does not represents huge limitations in terms of an assumption, because we can still model, for example, mutational biases. As you can see, this formulation sort of resembles the one that we do for the GTR model, or the general term reversible, and this is exactly true. However, we have to be careful because in POMOs, these represents the mutation rates, not the substitution rates. So the formulation is similar, but they are actually modeling completely different processes, okay? Another assumption that we do about the mutation rates is that we only allow mutations to happen at the boundary states, or the fixed states, as it is the case of this scenario here. And the reason why we do not allow mutations to happen at the polymorphic states is because when the mutation rates are really low, as it is the case for most of the multicellular eukaryotes, the boundary mutation assumption is usually a good one. However, when we start to observe higher genetic diversities or higher mutation rates, this assumption, or the boundary mutation assumption, might be violated. So for example, you have to be careful in using POMOs with microbial data, for example. Okay, now that we know how we escape the fixed states, let's see how we move along the polymorphic ones. And I have an example here. So again, we have Q, this is an element of the POMOs ray matrix, and I'm already at a polymorphic state. So I have n individuals with the AI allele, and after a period of time, I'm reaching a state where I increase by 1 the frequency of the AI allele, meaning that I decrease by 1 the frequency of the AJ allele. And this, of course, can happen due to several processes, and the first one that we'll see is genetic drift. So genetic drift is modeled according to the Moran model, in which one individual is chosen to die and one individual is chosen to reproduce at each time step. And essentially, genetic drift is represented by this coefficient here. And again, this is the number of individuals which have the AI allele. One of them will reproduce in order to increase the frequency of the AI, and one of the remaining individuals will be dying, and so the frequency of the AG allele will be decreasing by 1. So as you can see, if I would do the other way around, meaning if I would decrease the frequency of the allele AI by 1 and increase the frequency of the allele AJ by 1, I would have exactly the same coefficient here. So drift acts symmetrically or unbiasedly. However, we know that in most of the cases these processes are biased. There might be some advantage associated to the allele A or disadvantage, and we wanted to model it. So to do that, we use selection, and this is exactly the parameter that we use to describe selection, the parameter phi. So essentially, selection acts to favor or disfavor the reproduction of the allele in case. So for example, the AI is reproducing, so we add the element phi AI. And this can of course be higher than 1, meaning that it favors this allele to be reproduced in the population. It can be equal to 1, and if it's equal to 1, it actually doesn't really change the effect of genetic drift. Or it can be lower than 1, meaning that is disfavoring the reproduction of the AI allele. And this is how we will introduce some biases in our model. Of course, like the standard substitution models like the Jukes-Cantor, the GTR, POMOs are continuous time Markov models, and of course they are fully characterized by the rate matrix. And essentially, we use these two building blocks to fill in the POMO rate matrices. And in Rebase, we have a plethora of functions already implemented. For example, we have this very general case in which we represent a population dynamics with k alleles and n individuals that evolve with a certain vector of mutation rates and fitnesses. And we may additionally consider that the mutation rates are reversible, and in this case we have the reversible POMO kn. And in this case, we no longer see the mutation rate vector, but instead the base composition pi and the exchangeability rho. Another very frequent situation is that we assume that the 4 nucleotide bases A, C, G, and T are the 4 alleles in our population. And in this case, I'm just representing here a POMO ray matrix in which I know a priori that the number of alleles are 4, but it can also of course be other 4 alleles apart from the nucleotide bases, of course. In this case again we have mu and the vector of fitnesses, but we can also assume for the very same case with 4 alleles but now a reversible mutation model, and it's the same thing. We can also instead of using 4 alleles, we can also have the situation of 2 alleles, and there are also functions for 2 alleles or biallelic models. And finally, we have the reversible POMO 2 and reversible POMO 3. These are essentially the virtual POMOs, and actually we'll be using them today to do phylogenetic inferences. And long story short, these virtual POMOs try to represent the population dynamics that happens on a much larger population by using the smallest possible virtual population size. In this case, 2 virtual individuals, and in this case 3 virtual individuals. However, with 2 virtual individuals we cannot really identify selection, so it is unidentifiable. That's why you cannot see the fitness vector being defined as an argument of this function. However, with 3 virtual individuals, the selection coefficients are identifiable, and we can again estimate it. So these 2 models are quite handy because with one we can make phylogenetic inferences accounting for mutational biases but neutral, and in this case we can do inferences by additionally considering selection, and they are very efficient, computationally efficient.